With support from the Office of Naval Research, Virginia Tech has developed a series of open source learning simulations for radio frequency and wireless communications concepts, as well as for radio frequency spectrum sharing and spectrum agility. We'll be right back with a preview of one of the simulations.
Please see the video description for a full list of disclaimers, including the ones here, plus a timeline and helpful resources and links. Please support the channel by using our affiliate links.
To appreciate the importance of the radio spectrum, it's useful to understand the relationship between bandwidth, signal-to-noise ratio, which is related to signal power, and the maximum data rate that can be supported by a radio channel or transmitted by a radio signal. We've developed this simulation to let students and other learners see the information capacity calculated using the Shannon or Shannon-Hartley limit as a function of these other parameters of the signal. As you can see, there are 4 sliders that let us control transmission parameters and then also the noise floor or the noise level, something we generally don't have direct control over in a communication system, but it's useful for conceptual understanding. So you can see we control the frequency, the bandwidth, and the gain, which controls the amplitude or power of the signal. And we also can control the noise floor or the noise level, which you see as a horizontal line in the plot. That plot shows power spectral density in units such as dBm or dB milliwatts per hertz of bandwidth. And you'll see how the signal looks with different variations of these parameters, but you'll also see displayed in text at the moment the information capacity. And the information capacity is a fundamental limit that you can think of as a speed limit for data communications. And any practical system will have a data rate that's less than, but it may approach the limit given by the Shannon-Hartley law. We'll go ahead and vary some of the parameters and see what that does to the information capacity, which is shown right here in the simulation homepage. First, we'll vary the frequency. As you might expect, that doesn't actually change the information capacity because it's not changing the 2 parameters that the information capacity depends on. And those are bandwidth, or the range of frequencies occupied by the signal, and signal-to-noise ratio, which is related to the amplitude or power of the signal. So frequency doesn't have any effect at all. We also have the option here, just for purposes of the simulation, to change the noise floor. So you can simulate perhaps a receiver that's built with less noisy components or amplifiers that have a lower noise figure, for example. And you can also simulate noisier environments, and you can see how as the noise decreases or increases, the information capacity of the channel increases when the noise is low and decreases when the noise is higher. And you can also see the signal-to-noise ratio on the user interface, and you can approximate the signal-to-noise ratio by looking at the vertical difference between the peak of the signal in the signal bandwidth and the noise floor. So in this case, we have about a 10 dB, maybe 7 dB difference between the signal right here and the noise here, and we can see that that signal-to-noise ratio is 6.9 dB, so it's very close to what we would see. As always, you can zoom in using Control+ in most browsers, and zoom out using Control-. Soon we'll see another interactive simulation in the HLSI series. I look forward to seeing you then.
Thanks for your time. Please hit like and subscribe and support the channel by using our affiliate link if you plan to buy a featured item. We also provide consulting services and referrals.